Okay, guys, we are starting. Let me introduce to Aalto, who is a senior.
Ребята, мы продолжаем. Наш следующий докладчик Тату Aalto. Он работает над Northlight Engine.
Northlight Engine. Please meet him with applause.
Okay, thank you. So let's get started. So I'm Tatu Aalto from Remedy Games. You might know Remedy Games from games like Max Payne, Alan Wake, and now recently Quantum Break. This is a presentation about porting Northlight Engine to X12, so diving into fairly technical stuff. I hope you had some coffee. We gave this same presentation at GDC this year, a couple of months ago. Consider this as an improved version if you saw that one already. So I'm trying to cover what you need to know when porting Engine into X12. I'm going to go over practical topics that we met when doing our port. So this is not going to be low-level X12 API documentation, but list of practical things that you need to do when porting stuff over. I'll do small high-level stuff on Quantum also. So the Northlight that I mentioned before, it's the in-house engine we built at Remedy for the games that we do. The first iteration of engine was done for the Alan Wake. Now it's built to handle Quantum Break. Many things carried over from the past, but there was a fair bit of rewriting also done. So the Quantum Break is out on stores now. It's on Xbox and Windows 10. We ship both platforms using X12. I'll start with a short introduction on how we draw frame in Quantum Break. Like in Alan Wake, we use light creep as renderer. So it means we draw all the geometry twice. First, doing all the information that we need for calculating the lighting, and then the second pass for the final materials. The frame is started off by launching shadow rendering tasks into jobs. We create single async job per shadow map. Geometry buffers are rendered with MSAA and then downsampled using clusterization of samples. The list here shows the order of draw commands. We submit them into GPU. The CPU order, as we are doing multi-threading, doesn't match this one, but we do stuff on threads and then pull them back into main thread and submit. Next off is screen space shadowing. We have occlusion for diffuse lighting, and then specular. Also bent normals and sun shadows get filtered in screen space. Next, lighting. This is your typical directional lighting, and then sampling of pre-calculated global illumination. We use screen space techniques to add detail that's not captured well with the pre-baked data or the shadow maps. And as a result, we get consistent lighting on different scales, and it works for static and dynamic geometry. In order to get nicely anti-aliased image, we do the second MSAA geometry pass using MSAA by using reconstruction lookups from the previous geometry buffer rendering. We know which lighting samples correspond to which geometry samples, so we get fairly good quality even with the lower resolution lighting. Transparent drawing is divided into 3 resolutions in order to avoid heavy fill rate. And the final composition on top of opaque geometry uses the same reconstruction lookups as the normal geometry rendering. And the last thing, post-processing, I'll just cut it short here. We do motion blur, depth of field, distortion effects, game-specific stuff, quite a lot of here, but it's not really super interesting in terms of the X12, so let's not cover that here. This is the final image that we have in game, so this is captured from the game, just single frame. Here's the X12 checklist I'm going to go through. There's quite a many slides with lots of text. I'll try to be quick as we are short on time. So first off, Descriptor Tables. This is a very key part to consider when doing the X12 port. Single table holds all the resources that GPU sees. You need one table per draw call, and you can reuse them when the GPU is done working. Dynamic resources you don't have anymore in DX12. You need to do double buffering and that stuff in your application. Previously, it was possible to call map discard on resources and let the driver handle the memory lifetime. Now you need to do it by yourself. This is not really super hard, but it takes quite a bit of time depending on complexity of your engine. Pipeline state objects are, using them is easy. Creation is the problem, at least for us. In ideal case, you want to create pipeline state objects in export time, but it means that your engine needs to be done in such a way that you can actually know everything needed in the export time. So that would include shader code, different vertex input layouts, blend types, rasterizers, that kind of stuff. For us, we didn't really have time to do that big engine refactoring, so we create pipeline state objects when we encounter new states in the game, and then try to cache as much as possible while inside loading screens. For us, we have roughly 500 unique PSOs. They take roughly 200 milliseconds to generate, so you definitely don't want to generate them in between of gameplay. So this is what you need to know in order to create pipeline state object. Command lists are a new concept in DX12, although we had immediate and deferred context in DX11. It's exactly the same, it's just only one class now. It only has memory allocation decoupled from the actual class. Resource transitions are next to memory management, the other big thing that you need to be doing. So in DX11, driver handles all the resource transitions. In DX12, you need to do it by yourself. Depending on hardware, transitions can be costly. They might introduce fast clear expansions, depth decompressions, that kind of stuff. You really don't want to make too many transitions. We keep current state next to resource and switch on demand. This is close to what DX11 drivers do also. It means that it adds some overhead, but it can be fairly messy to do it completely manually. Especially with the multi-threading, it can be complex. Some stuff missing, as the dynamic resources are missing, you will end up using lots of staging resources. You really need to consider the timeline on CPU execution and the GPU execution to actually figure out how to best port your existing stuff into DX12. It is so that double buffering is not enough in all cases, depending on your time framing, and it can cause fairly hard to debug bugs. And related to allocations, small resource allocations by default on DX12 operate on single heaps, which means that every small allocation will take 64 kilobytes of memory. This is obviously something that you don't want to ship with. If we disable our small resource allocator, we lose something about 300 megabytes of memory immediately. While doing the allocator by yourself, it would be nice to be actually going to console style, having just big buffer that you defrag, but that's not really possible with the DX12 because evicting system of operating system manages everything in heaps. So if you make really big heap, you might be in problems, but I'll cover that later. Generate mipmaps, one thing that's missing in DX12, you need to write it by yourself. Good side is that it's fairly easy to actually make faster by yourself. Or exactly, it's actually really hard to actually make slower than you have in DX11. Now resources, you can't use them anymore. You need to create specific typed resources that you bind instead of nulls. Doesn't sound like a huge deal. For us, it meant that we need to carry quite a lot of pipeline state to quite end of the binding process. So it adds overhead. You will practically end up doing the same stuff as DX11 drivers are doing automatically for you already. Counted append buffers don't exist. I don't think many people use them. We happen to have one. It's easy to replace them with atomic increments and small buffers. Queries, one thing to consider, you can't really allocate anymore in the same way as you used to with the previous APIs. You need to make bigger chunks of queries and manage the memory there, otherwise you will be in problems. So residency is one really big topic on DX12 that you kind of don't need to do to get started or to get image into screen, but unlike in previous APIs, DX12 gives you control on what to evict and what to keep resident. So you need to actually inform operating system how to throw resources out of memory if you happen to run out of memory. And on PC, you obviously run out of memory because there can be other applications running and so on. We actually haven't nailed perfect way to do this. In order to match what DX11 does for you automatically, you will need to track usage of all the resources, evict the ones that haven't been used for a while, and make sure that you make all the resources resident before you submit them into command lists. And the catch here is that unfortunately it's not enough to actually do that because operating system can always override what you've done. So it can actually throw whatever resource out of the memory whenever it wants. And if you have, for instance, created gigabyte of texture data into some buffer, operating system can actually go and throw that gigabyte buffer away. And that's going to be many milliseconds. So, to sum it, you're the driver now in DX12. There's quite a bit of work needed in order to match the performance of previous APIs. It's not rocket science, but it's not trivial either because there's so much of it. It takes quite a lot of time to do it. Resource transitions and memory management are definitely the hardest ones, at least for us. As usually, it makes sense to focus on the optimization on bottlenecks, but DX12 is really all-in type of API. You can't really choose your paddles. You need to do it all, otherwise you're screwed, and you can't really ship without implementing everything. And CPU and GPU timelines, because you need to manage memory manually, you need to be aware of timings on CPU and GPU. Previously, it has been possible to just not care about that stuff. Now you really need to start thinking of different timelines on CPU and GPU. So next I'll go over some high-level designs on how we ended up doing DX12 in Northlight. These are tied to our earlier engine design, so this isn't really our recommendation on how to do it, but I hope it gives you some context. We are a relatively small team, so we usually aim to keep things simple, target small amount of platforms. This time we were on DX11 and we need to be still using DX11, so we made DX12 fit into what we had already. We started off by doing DX12 both for Xbox first. The reasoning for that is that there was just less unknowns for us. There was better tools, drivers were in better shape when we started, so that was our decision. Still, I'm not going to be going into platform-specific details in this talk. I'll start off with resource barriers. So the transitions, we ended up implementing half-automatic system for doing transitions in Quantum Break. We automatically transition on main thread, but do transitions manually on the ASIC jobs that are drawing lots of geometry. For us, this is practical because all the heavy lifting of rendering is running in threads anyway, and the dependencies are actually fairly easy with normal geometry rendering. In main thread, we have tons of dependencies to different resources that are rendered earlier, so it's really nice to have some automatic system for that, even though it costs something and you actually end up wasting performance and going kind of like backwards towards DX11 style rendering. As I said, making too many transitions will kill your GPU performance. It might be not easy to see it actually with the tools that you have out at the moment. On CPU, transitions don't cost pretty much anything. On GPU, they do cost, depending on hardware. So you will actually need to be testing on different platforms to see what happens. Jumped over. So drawing. Drawing is probably the most, the part where the biggest CPU wins could have been made if we were starting to rewrite stuff. With this project, we didn't really have time to do it, and we wanted to keep DX11 still alive, so we didn't go there. But that's where you actually are going to seeing wins if you refactor your engine. So we execute draw calls in the same style as before and catch all the resource binding calls. By tracking previously bound values, we find situations where the PSOs change and calculate hash from the state that it changed to and just grab one from the cache. That's pretty much it. PSOs are easy to use, as I said previously. Their creation is the problematic part. Using is easy. You just create them and forget. Then something about threading. Our engine was fairly heavily threaded already on DX11. Going to DX12, there isn't actually that much modifications if you have been using deferred contexts in DX11 world. Pretty much the only thing you need to do is to add the resource barriers, which can still be annoying, but it's not super hard. So we record individual command lists on different threads and execute them in specific order on main thread. The ordering of how you create resources needs some thought with threading, but that you need to do with any API anyway, so it's not going to be anything new. Here's the figure, what we do at the moment. So the green lines represent work that happens in thread. Blue lines are work in main thread. We start work on async job. When we start working on async job, we initialize a bunch of thread local state. Then we record a bunch of draw calls into command lists, and then return the results with some cleanup state to main thread. And later in main thread, we execute these command lists. We pull our descriptor table managers. In thread initialization, we pull single manager for each thread we use. Manager then handles table rotations, allocates more space, and so on. We also pull command lists and allocators in similar way. So in thread initialization, we acquire descriptor table manager, fence for it, command allocator, command list. Then we go on, record a bunch of command lists. Then in the end of the thread, when finished recording stuff, we release CPU reusable resources. So that would be descriptor manager and command allocator. And then on main thread, later when we actually execute stuff, we can release rest of the stuff. So these guys need synchronization with the GPU. So that's why you need to get fence values from the main thread. And that's actually already last slide. So in conclusion, on GPU performance, you really need to do things right to match DX11 performance. It's not easy thing on all architectures. Messing up memory management can cause huge stuns in your frame rate. On the other hand, on CPU side, it's fairly easy to outperform DX11. It's almost impossible to make it run slower. But it's a good question that are you actually API bound? I mean, we are doing a couple thousand draw calls per frame. In that it doesn't really show. With DX12, it's slightly faster. We gained maybe 5% or so, but the difference is not huge if you're not API bound. Of course, if you do lots of dynamic stuff and make 10,000 draw calls per frame, then yes, definitely makes sense. But not for smaller amounts. The wins will be small. That's it. Thank you.
Thank you. Okay, guys, let's move to the Q&A section. So if anybody has any question, please don't be shy.
Hi, I have a memory management question. I have a memory management question. How do you handle the virtual space limit on first tier DX12 hardware? I mean, on certain video cards, the driver virtual space is limited to 2 gigabytes, and any resource allocation that goes above 2 gigabytes essentially gets your driver shut down by the operating system.
I think that's exactly what happens.
Yes,
driver shutdown.
How do you manage that?
I mean, yeah, 2 gigabytes is below our minimum spec actually. So
you just keep all the resources.
Yes, we don't actually manage it. We try to minimize. We have options to go low on memory size. That's pretty much all we are doing. We don't have anything special for that stuff. And as I said, it's not really possible to create. I mean, good way to do it would be to have just big chunks of memory, but that doesn't really fly because eviction can happen, and so you usually should keep heap sizes under like 50 megabytes or so. That's roughly the size that you can actually pull inside frame without getting huge stuns.
Okay, another question from here.
Hello.
How do you handle multi-GPU stuff? Does it add another level of headache above what you have described, or is it not much of a problem?
Well, in terms of API, it's actually easier than ever because you actually have control on what gets executed on which driver, which GPU. So you actually can do it by yourself. You don't need vendor-specific drivers anymore for that. But we are not implementing that stuff. Actually, it's out of scope in Quantum Break. We just simply didn't have time or resources to do it. But it would be possible to do it with the X12, and it's actually quite nice way to do it.
One last question.
Thank you for the presentation. And were you actually API bound? And what benefits did you get from moving to the X12?
So we started off the project by defining that the content will not go over 2,000 row calls or so. So that's the amount that we have been seeing that you can push with fairly good confidence through the DX11 and previous APIs. So we didn't actually have that many API calls to start with. So yes, we are not API bound. We are bound by our own stuff. The second question, what did we get from DX12? Well, now we are in DX12. It's not a huge win.
Okay, thank you, Tatu.
Okay.
Well, let's applause, guys.
Thank you.
If anybody has any other questions, you can go straight to Tatu and ask all of them. And we are coming back just in a few minutes with the next presentation. Thank you.